So let's continue to consider this nonlinear advection equation here. And we'll take it with an initial condition phi. And we'll assume that the wave speed is increasing with density, like we talked about before. And we'll also put some technical assumptions on our initial conditions. So we'll suppose that it's non-negative, but that it's going to be a decreasing function. So that might look something like a decaying exponential function, like this, or maybe something like a Cauchy distribution, like this. And now what we are interested in is when the gradient of the solution can blow up in finite time. And so this is, by gradient, I mean the x derivative or space derivative u sub x. This can tend to infinity, u sub x tends to infinity as t approaches some finite time t sub b. So how do we find when that time is? Well, let's go back to the characteristic curves that we had for the nonlinear case. So remember, these are defined implicitly by this equation x equals c times phi of psi t plus psi. And then we can differentiate this with respect to x. And we see that on the left side, we just get a 1. And on the right side, by chain rule, we have c prime phi of psi times phi prime of psi times psi sub x times t plus psi sub x. And so we can solve this for psi sub x. All we need to do is factor out the psi of sub x from the right side here, and then divide the resulting thing over to the left-hand side. And so it's going to end up looking like psi sub x is equal to 1 over 1 plus c prime phi of psi phi prime of psi times t. Okay, now if we go back to the other equation that we had for the nonlinear advection case, that one is the one that tells us that the solution u is equal to phi of psi, where psi is determined by that relation we had in the previous line right there. Okay, so I can also differentiate this guy with respect to dx, and that tells us that the partial of u with respect to x is phi prime psi times psi sub x, which means that we just need to multiply phi prime against the deal that we got in the previous line. And so we're going to have phi prime of psi over that same crazy denominator of 1 plus c prime of phi of psi, goodness, too many Greek letters, times phi prime psi times t. And then the question is, when or where does this blow up? I guess actually that should be when does this blow up, because we are talking about the t variable here. So the gradient catastrophe will occur at the minimum value of t, which makes the denominator 0. And so that means that we need to look for the first time, or the first value of xi. That gives us negative 1 over phi prime psi times c prime phi of psi. and this should be a non-negative value. Then this special value t sub b, this is what we call breaking time. So if we go back to the example that we were working on before, where we had c of u equal to u, and phi of xi equal to 2 minus xi, as before, then differentiating these guys is going to give us c prime of u equals 1, and phi prime of xi equals minus 1. So we can immediately compute t sub b as the minimum of the constant quantity minus 1 over negative 1 times 1. And so the negatives cancel, and it's just equal to 1. So breaking time is equal to 1. So that's when breaking occurs. And we've just recovered what we saw in the previous video.